first homework assignment had two problems, and the second problem was as follows. American Airlines leases a 300-seat carrier to fly its daily Dallas to Denver route. Recently lowered its ticket price and observed the following demand for seats by business and tourist class passengers. At a price of $200, we had a quantity of 180 passengers, 130 were business passengers, and 50 were tourists. At a price of $240, the original price, we had 100 passengers, 90 were business, and 10 were tourists. It is clear that the revenue with a common price is higher when the price is lower. So we had a larger quantity, 180 times the price of 200. That gave us a total revenue of $36,000. At a price of $240 with 100 passengers, the total revenue was $24,000. The problem gives us three possible aircraft: a 300-seater with a daily fixed cost of $32,000, a 260-seater with a daily fixed cost of $28,000, and a 180-seater with a daily fixed cost of $20,000. It is clear that the maximum number of passengers here is 180. So under the conditions that we are studying, it would not be necessary to use the 260-seater or the 300-seater. Notice the cost savings. We are then told that the cost to service each passenger is about $20, regardless of the aircraft that's being used. This is the marginal cost of putting a passenger in a seat. And we can see that if we use the 180-seat plane, we would save $8,000 over the 260-seat plane and $12,000 over the 300-seat aircraft. We've only considered two prices thus far. The real question we want to ask is what price will maximize the airline's profit. It is unambiguously true that price discrimination will increase revenues. And we only have 2 points here, so we're going to have to extrapolate from the known region, two prices, two quantities for tourists, two quantities for business passengers. And we will use those 2 points to derive a straight line, and that straight line will be the demand curve for tourists, and another straight line, which is the demand curve for business passengers. Okay, so we're going to take the known data and then try to sketch the known parts of the demand curve before we extrapolate into the unknown regions. We're going to locate a price of 200. Then we're going to identify a price of 240. We're going to plot those 2 points. So approximately the demand for tourists and the demand for business will be what you see here on the graph. We've already determined that the disaggregated demands will yield different prices, and as a consequence, we would end up making more revenue. So we're going to sketch these 2 curves from one axis to the other, and we're going to look for the midpoints of these 2 demand curves, and that will tell us where we would maximize revenue. However, maximizing revenue is not the goal here because we are constrained to carrying only 180 passengers. So the question then would be, what prices should we charge when we have 180 passengers as the maximum quantity? How should we allocate the seats between the 2 types of passengers, and what prices would be determined as a consequence? From the known data then, we would extrapolate and obtain the demand functions P equals 330 minus Q. That would be the business passengers. And for tourists, our demand curve would be P equals 250 minus QB. These are sometimes known as inverse demand curves if you have P as the subject of the equation, and demand curves if you have Q as the subject of the equation. Suffice it to say that we then multiply the price by the quantity. That gives us the revenue. So we have 2 revenue functions. So we get the revenue for business passengers, RB equals 330 QB minus QB squared. And the revenue from tourists would be RT equals 250 QT minus QT squared. Because we're going to substitute for QT equals 180 minus QB. Then we have the expression that you see here with the QB terms So the expression in the second square bracket is the revenue from tourists, or a function of QB. So we can differentiate that and set it equal to 0, and that would be saying from this revenue function we're going to try to find the maximum on that revenue function. In other words, when we take the first derivative, we're asking what is the slope of the revenue function, and where is the slope going to be equal to 0 at the top of the revenue function. So after we differentiate, we come up with the equation 440 minus 4QB equals 0, which tells us that QB is equal to 110. Because we have 180 seats available, if we allocate 110 seats to business passengers, then QT will be 180 minus 110, which is 7. We're going to plug those quantities, 110 and 70, into the inverse demand functions for tourists and business, and we will obtain prices 220 for business and 180 for tourists. Price times quantity is revenue, so the price of 220 for business passengers and the quantity of 110 business passengers, so the revenue from business passengers is 220 times 110. The revenue from tourists is a price of 180 times the quantity of 70. The total revenue is $36,800. Notice that that's $800 more than when we charge a single price. So was the price discrimination worth it? Well, it depends. The question with price discrimination is that it will always give you a higher revenue. So then we have to ask the question, was it worth the cost of price discriminating? How much effort and time was taken to segregate, to collect data, and figure out how we should charge the two different groups, different prices? And if we spent more than $800 trying to do this, then the price discrimination was not worth it because the cost of price discrimination was greater than the extra revenue from price discriminating. Suffice it to say then that we have total revenue of $36,800. The cost is $23,600, and that gave us a profit of $13,200. Again, if the price discriminating had a cost, and we had to factor that cost into the equation, we would be asking the question, was it worthwhile to price discriminate?